Hi there, you're in the lab with your mate JJ. Today is Learning the Art of Electronics Day. Today we're going to be learning the art of electronics. My silly job title for today is Tech Lead. Today I'm the Tech Lead. And Tech Lead's not such a silly job title at all. I probably am a Tech Lead. Some of my friends would be. So yeah, today we're going to keep on keeping on. We're working through our book, which is of course Learning the Art of Electronics, a hands-on lab course from Thomas C. Hayes and David Abrams, with the assistance of Paul Horowitz. So today we're going to continue. Last week we had a look at the Thevenin model, and we actually built the Thevenin model. This week we're going to be applying Ohm's law to convert a meter movement into a voltmeter and an ammeter. So we'll see how we go. There's three things to do there. The first one is to measure the internal resistance of the movement. Then the next thing is to make a voltmeter, and then presumably after that we'll be making an ammeter. Not sure about that. Doesn't say anything about it. We'll see. Anyway, and I'm not 100% sure if I'm going to get the notes, the theory component done in time for the video, but we'll see. We'll see how we go. But what we're definitely doing is the prac. So we're going to pop over to the bench. And I'll show you the meter movement that I'll be using, and then I guess we'll just proceed through the work. So over to the bench we go. Here we are on the bench, and I'll just grab the textbook. This is the textbook. Let me just tell you what we'll be doing. So the Thevenin model is extremely useful as a concept, but you'll not again build such a model. The circuit you just put together, which we did last week, is useful only as a device to help you get a grip on the concept. Now comes instead a chance to apply Ohm's law to make something almost useful, a voltmeter and then an ammeter, which is a current meter. You will start with a bare bones meter movement, a device that lets current deflect a needle. So let me just show you what we've got. I prepared this a while back. I haven't used them yet. I knew that I'd be doing this course, so I got myself a whole bunch of meters. The ones on the left here are ammeters, and then the stuff at the back and along the side is voltmeters. Apparently we'll want a very low ammeter for what we're doing. So I've picked a 100 microamp meter, which is the smallest meter that I have in my collection. So we're going to be using that for our experiments. That's this here. And I should say, I've put on the back, I've put on some bolts, and I've got these banana plug spade or lug adapters. So the idea is I'm going to stick them in there and then tighten them up, and then I'll be able to run banana plugs into the meter for testing purposes. So we'll be doing that together in a little while. So, as it said, you will start with a bare bones meter movement, a device that lets a current deflect a needle. This mechanism is basically a current measuring device. The needle's deflection is proportional to the torque developed by a coil that sits in the field of a permanent magnet, and this torque is proportional to the current through the coil. See the sketch in figure 1L.4.1. So this is a picture of the permanent magnets around the outside, and the moving coil on the inside, and some springs for control purposes attached to a pointer which will deflect. So, and there's a note here. Oh no, the note's not important. An analog multimeter, or VOM, volt ohm milliammeter, is just a movement with suitable resistor networks attached. We would now like you to reinvent the multimeter. So just to interrupt with what I've learned so far, and I don't know the exact numbers, but I think if you want to operate a meter movement as a voltmeter, that you want to add series resistances, and if you want to operate it as an ammeter, you add shunt resistors. I believe that's the case. I don't really understand those things yet, but that's basically some of the stuff we're going to be trying to learn today. So that's the introduction to Ohm's law applied. Now we're on to 1L.4.1, which is about the internal resistance of the movement. So it says here, you could design a voltmeter, as you will in the next subsection, simply assuming the movement's internal resistance, Rint, is negligibly small. The resistance of the movement is low, well under 1 kilo ohm. But let's be more careful. Let's first, I'm not sure what they're using, because I heard that the 100 milliamp things that I'm using, they're maybe 2 or 3 kilo ohms. Anyway, we'll find out, won't we? And I've got choices of ammeter. I could pick one from the milliamp range instead of the microamp range that we're using. So maybe we'll learn something as we go along. But let's be more careful. Let's first measure the internal resistance. And I already read this and I didn't understand what he says next. He says, here, please note, we want you to work with a simple bare meter movement, not with a multimeter. It's more fun to start from scratch. And then, so he just says that they want us to not use a multimeter. And then in the next paragraph, he says, do this measuring any way you like, using the variable power supply, digital voltmeter, or a VOM if you need it. If you use DVM as current meter, we should warn you that it is easy to blow the meter's internal fuse because a moment's touch to a power supply will pass an essentially unlimited current. To make things worse, a DVM with blown fuse offers no display to indicate the problem. Instead, it simply persists in reading zero current. There are several good ways to do this task. Good ways to do what task? And didn't they just say, don't use a DVM and then do it any way you like? So that's really quite confusing. Anyway, what I'm going to do to measure the internal resistance of the movement is I'm going to use a resistance measurement on my multimeter and see what it says. I don't know if it's I don't know about reactance. I don't really understand that yet, but there's no frequencies involved, so I don't think it's going. I think it's just going to be a matter of just hooking up the multimeter in resistance mode and checking the resistance. I think that'll work. I'm not an expert though, but we'll do that and we'll find out. And he goes on to say the meter movements are protected, and he's talking about the meter movements that they use in their lab when they deliver the course. Of course, I don't have access to their equipment, so I followed this note down here, note to instructors. Please add 2 paralleled and positively oriented silicon, oppositely, yeah. Please add 2 paralleled and oppositely oriented silicon diodes, such as the 1N.4.1 in parallel with the meter movement. These will conduct at about 0.6 volts, protecting the movement during overdrive. So we're going to make a circuit with these diodes built in, I think. So on we go. So don't worry about burning out the movement, even if you make some mistakes. Even pinning the needle against the top will not damage the device, as we found by experiment. Though in general, you want to avoid doing this to analog meters. We have provided diodes that protect the movement against overdrive in both forward and reverse directions. You should note, as a result, that these diodes that protect the movement also make it behave very strangely if you overdrive it. No doubt you can guess what device it behaves like. And honestly, I can't, except a short circuit. Like if you exceed the forward, if you deliver the forward voltage or more, then the diode will just conduct it and it'll be a short circuit. But a short circuit's not really a device, is it? I don't think it'll behave like a resistor. Certainly not going to behave like a capacitor or an inductor. I don't know. I mean, a transistor's kind of like 2 diodes, but you can't make a transistor out of 2 diodes. So I don't know. I don't know what it behaves like. Maybe it behaves like a short circuit. That's my guess. If you know, I'd love to hear from you. And it says here, so don't use data gathered while driving the movement beyond full scale. I was thinking actually we will drive it beyond full scale and we'll get some measurements and we'll try and see how that diode's behaving. Get some clues. So it says here to sketch the arrangement you use to measure Rint and note the values of Rint and I full scale. Well, it did say I'm a bit confused. That there are some things that we're allowed to use the DVM for, but not the measurement of resistance. I'm not sure about that. I'm going to take a quick break, get more coffee, and we'll be back. All right, well, I'm back and I've got my coffee and I've got the rectifier diodes. I haven't got heaps of 1N.4.1s, which is the one that they recommended 1.4.0.0.4. Yeah, I've got plenty of those, so that's what we'll use, just per the recommendation. But I'm pretty sure we could use basically anything. We're just relying on the forward voltage. Anyway, so we've got our resistors. We're going to need the old iron on, so I'll put the soldering iron on. I'll put this out of the way. And let me show you. We're going to be using the old Electro Cookie printed circuit board. So that's one of these from Electro Cookie, who make them. They're soldered. They're like breadboards, but they're for soldering, which is I find quite handy. I've got a swag of these. So what we're going to do is attach our movement to banana cables with those. I'm going to run the banana cables into here using some pin header, which is here, and a whole bunch of it. I might even go polarize. So let's do this together in time lapse. So let's do that together now. All right, so I've made a little circuit board. It might need some improvements, but it's got the parallel and reverse polarity diodes installed, which will protect the meter. And we've got the meter up the back here and these adapters for banana plugs. So let's just quickly install these. All right, I think I need extra washers, and I think I have some in here. I do indeed. So those are big honking ones. Don't need something that big. Oop. All right, well, that took a bit of doing, but I think we got there in the end. Now, I don't know how low my power supply can go. How do we test this thing? I'm not sure. Let's put, I don't know, what are we going to do? Put 0.5 volt into it. How do we do that? I'm not sure. Need a resistor. I'll be back in a sec. All right, I'm back. Now we've got the banana sockets attached to the movement. What we're going to do next is put some pin header on here. And we're going to do it how are we going to do it? We want to be able to put something across here So what we got up the back here. Okay. Well, let's do 3 again. 3 and 3. One and 2 and 3. Alright, so we're just going to solder that in. I'm slowly getting my technique down for putting the pin header in. What I do is just put it in and then hold it in place on the left hand side with the blue tack, and then once I'm happy with that, I can just pin one side that doesn't have any blue tack on it, and then I can do the other pins after that. So we're going to do the same thing over here. Actually, you know, I'm going to use a different color pin header. Not red. There we go. Green. Green's good. So I'm going to actually take this out now that I think about it. Just chucking in the scraps. So we'll just do 3 again. Or we could do 4. Is there any reason not to do 4? Not really. Shall I do 4? Sure, I'll do 4. 1, 2. No, I'll do 3. Because I don't want to connect them all up if I don't have to. And 1, 2, 3. All right. Well, let's see if I can get that in there with the solder there. In you go. I might need to get the old solder sucker out. I think I will. All right. So where is a solder sucker? Here's one. Now, which socket is it? This one. Ah, dear me. Too little, too late. I'm going to break out the big guns. I've got a desoldering iron. So we'll just let him heat up. And let's see if we can get him through there now. No. 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 Doesn't seem to want to go. I suppose the other thing we could just try is some solder wick. That is, after all, what it's for. So let's try that. Turn the iron back on and the desoldering off. There we go. That got him. So again with the blue tack, let's fold him in there. All right, there we go. Let me just show you that. Show that quickly. So this is the new board. On the left-hand side, it comes into 3 green terminals, which I'm going to have to join to each other. Then that runs into a jumper to hook it over to here, and then the diodes are here to protect the meter movement, and then it's symmetrical on the other side. The meter will go in here, and then the inputs will come in here. And if we want to, we can intercept them and get a current measurement or something like that, if that's what we want to do. Now I've got to finish this. I've got to put in the extra wires, so let's do that quickly. So I probably don't need to do what I'm just about to do, but I figure I'll do it anyway. This particular board, I want to put some female pin header as well, because my potentiometers have male pins coming out of them, so they could go into breadboards. And I've got some pin header for the job. In fact, I've never used this type of pin header before. I only purchased it recently. Previously, I was using this stuff, which is really awful for chopping. It's so hard to get just the right amount of bits off, and it goes all flimsy and the bits fall out, and it's just yuck to cut it. So I think these are going to work better. Let's just see if I can get a male pin in there. Not really, actually. I was expecting that just to pop in. No, that's... is it working? It just barely kind of almost works. What about my other jumpers? I really want something that works with these jumpers. That's disappointing. Oh no, there it goes. All right, cool. Well, it's just a matter of pressing really hard. Pressing hard I can do. So we're going to join up say 1, 2, let me count them. I'll do this actually quickly. Let's do this and I'll be back in a sec. All right, so now we've got male pin header on the top, and we've got female pin header on the bottom. And we've got a jumper for connecting each side. So what we can do is take the jumper off and then plug in a potentiometer. So let's get a great big honking one. Well, we've got 10K, 100K, 1 meg. 1 meg's pretty honking. What's this one? This is also 1 meg. Interesting. So let's put our I'll clean up quickly. I'll be back. All right, I'm back. So what we're going to do is put the multimeter in resistance mode, and then we're going to get some banana fin to female, and we'll just put the cables in, and we'll make sure it's on ohms. There we go. That's auto ranging ohms, and let's just plug it in to our potentiometer. All right. So that's up at 1 meg all the way on. And if I turn it down, it can go down as low as 2 ohms. So let's turn it all the way up to 1 mega ohm. So, yep, okay. And now what we're going to do is pump some voltage into it. Oh, I've got a phone call. It was a spammer. It's always someone trying to scam you when the phone rings. Isn't that sad? All right, so we've got our 1 meg potentiometer turned all the way up. It's at 1 meg. If we turn it too low, we'll fry our meter movement. Although there is the diodes in place, so maybe that will save the day. We shall see. So we're going to need some power. Let me turn on the old power supplies. How much power are we going to put into this thing? Let's just say 1 volt. So V set 1, enter. All right. I'm going to put over voltage at 0.0001. I don't know how accurate that's going to be. Anyway, what happens if we turn it on? Okay, it says it's delivering 1 volt roughly. Okay, so let's get some banana cables to power this thing. How are we going to do that? I don't know if the colors are the right way around. All right, well, anyway, we're going to need power. So let's get some power leads happening here. All right, so this is negative, and I'm just going to run negative into this side of the meter, and then I'm going to run positive through to this side of the meter, and we're going to take the jumper off. That jumper there is not connected. It is connected on this side. It's not on that side. Now we're going to need to connect our meter. So let's stick with the colors that we've, the colors are wrong. Oh, well, let's see what happens. We can fix them in a minute. All right, so if we pump 1 volt into this with the potentiometer installed, all right, I'm going to turn it on. Can you see that at the back? I hope you can. I wonder if I can get you a bit closer. What about that? Yeah. So the bit that we're interested in is this bit. Can you see that? Doesn't want to sit flat. See if I can blue tack him in a bit. Can you see that? Yeah, okay. So the meter's turned all the way up. That's good. All right, on we go. 1 volt. All right, so it's delivering 1 volt. It's got 1 mega ohm over its pins. So let's turn the resistance down. Okay, I was expecting to see something by now. No. Nothing. What have I done wrong? Oh, we've got the polarity the wrong way around. Right, turn that off. All right, so in fact, all right, so we've switched the cables around. On we go. Now, if I turn this down, that microamp should go up. Yep, there it goes. Whoa. All right, so I don't know. Oh, shit. We don't want to go too far. There we go. All right. Cool. So it says it's 20 microamps. 20 microamps. Let's make some notes. I'll just clean up quickly. All right, I tidied up a little bit, and I just wanted to get my notebook out so that we can make some notes. Let's see, what have we got? What's today? It's the 2nd of the 12th, 2025. I've got a nice sharp pencil. I put the day first because I'm an Australian. This is learning the art of electronics. 1L4, 1L4. And I think I'm going to start numbering the circuits that I make with the circuit number. And I can make notes about them. So let me think about that. All right, so what I've done is I've started a naming scheme, and it's good. It's going to be good for about 1,000 circuits, and it's a JJ, and then three. I could make them hexadecimal, but I'm not going to. It's JJ and then 3 decimal digits. Good for 1,000 custom circuit boards. I'm going to document the JJ circuits. Over on in the lab with JJ. So let me just attach this. All right, so I've labeled this thing now, and I've just labeled it movement interface. So we can put the movement in and then see what it does. So again, we should power it up, goes to 20 microohms. So let's say V equals 1. I equals 20 microamps, and V equals IR. R equals V divided by I. R equals V divided by I equals. Now I've got to get this right. This is 0.00002 amps. So let's do. Oh, that's the wrong thing. What do I want? I want the calculator. All right. So we're going to go 1 divided by 0.00002 equals, that's 50K, 50,000. 50,000 equals 50K ohms. And we should be able to get our multimeter and measure the potentiometer in its current setting. So we can do that with the other one because we're going to need some free probes. How are we going to probe it? Let's use hook clips. Hook clips to the rescue. So we'll put this thing in ohms mode. And we'll just make sure it's in ohms mode, and it is. Very good. And let's see what happens if we measure the ohms of a short circuit. Not very much at all. Great. So let's take one of these out, and we could take both of them out. And let's just hook it up and see what it's set at. Should be about 50K. Let's see. So it says, oh, that's interesting. Oh, there we go. 48.7. It's actually moving around a little bit. Okay, 48.6. Very close to 50. Measured with fluke equals 48.7K ohms. All right, well, I'm pretty happy about that. So I'll just put him off, put him in the corner. So where does that leave us? We've got our movement interface board built. We can inject a resistance over here. We just put in 48 kilo ohms, 49 kilo ohms, roughly 50 kilo ohms, which and the meter agreed with us. So next we'll get our variable resistor over here, this great big honking thing. And we're going to try and figure out the internal measurement, the internal we want to know the internal resistance of the movement. Now, I have to say, it was a bit unclear about what he wanted us to do, because he said, do it without a multimeter, and then he said, do it any way you want. So that's a bit difficult to interpret, isn't it? Anyway, so, oh, and by the way, happily the things worked out. It is positive on this side and negative on this side. So that was fortuitous. And it is actually a bit odd, because you would have thought that the thing would flow from left to right, but in fact it flows the other way. Anyway, so we want to measure the I was going to get some straight up banana cables, and we'll put him back in measurement of ohms, and we'll unplug our circuit just temporarily. And we're going to need some banana plugs. We've got plenty of those. So we'll put positive on this side, negative in there. All right. Oh gee, maybe I shouldn't have done that. Hopefully I didn't fry it, because I didn't connect it through the I don't know. I don't think you can. If you try to measure it with the, I don't really know what to. Anyway, let's do it again. Hopefully it's not going to blow everything up. All right, and it says 2.27K. Can I hold that? Hold. I'm a bit worried we're putting too much juice into it. So we'll say okay, let's just line that off. And 100 microamp meter movement resistance as measured with fluke 2.278 kilo ohms. There you go. So what do we think about that? That sounds about right, doesn't it? They did say to expect something like that. So I don't know how much current this thing dumped into that while it was doing its resistance measurement. Anyway, the prac here is to measure the resistance, but if we measure current and voltage, we can calculate resistance. I'm going to take a break. All right, so what we're going to do is we're going to take a positive supply of 1 volt, and we're going to send it into a resistor called RS, the series resistor, and then we're going to send that into the meter. How do you draw a meter? Let's just draw a circle. There's something that goes in it, but I forget what it is. And here, so we're going to get VM, the voltage across the meter here, and then we're going to get the IM here, and then we'll connect that to minus, or I guess I should have just drawn ground, you know what I mean. All right, so for our series resistor, what have I done with my resistor box? Here. Okay, so for the resistor, I'm going to use 50 kilo ohms, which is 20 kilo, and 20 and 30 is 50. So, and we're going to hook that up so that it goes in on the left-hand side. So we don't need that for the moment. We're going to need some banana to, what have we got? So this is our 50K series resistor, and we're just going to put that over here. All right, and it's going to go in between these pins, which is very good. All right, so we've got 50K in series with the meter movement. That's not fully plugged in at the moment, so let's plug him in there. All right. So now if we were to turn this on, I think we should expect to see it to go to 20 microamps. So let's try that. Okay, something's wrong. What have I done wrong? I've got to connect the meter movement. So that was a mistake. Wasn't fully wired correctly. Where has he gone? Over here. Yep. All right. So let's try that again. When we power it on, should go to 20 microamps, and it did. I hope you can see that. I'll just zoom in quickly so you can see it. That's reading 20 microamps. Can you see? Yeah, 20 microamps because it's got 50K in series with it. So the other thing we want to do is measure the current through the system, and it should be so we've got two measurements we want to take. One is we want to get the voltage across the movement, So we'll use the EV blog BM2257 and we'll put it in voltage mode. Okay, and we'll connect the positive voltage here and the negative voltage here. Okay, and we're reading 0.041 volts across the can you see that? I'm not sure if I put this up if you'll be able to see it. No, you can't really, can you? What about that? Can you see that? Yeah, you can. Good. All right. So we're measuring across the meter about 40 millivolts. And we've got a meter over here, which I'm going to put into current mode. So let's put that in current mode. Where is current mode? And we're going to want to measure microamps, I think. So let's try that. And we're going to, oh no, these are the wrong types of connections. All right, I'll put these away. We don't need these at the moment. So let's try these. That's there and there. Now I'm going to turn the power off. I'm going to disconnect the jumper and then I'm going to connect, oh, I also inadvertently disconnected that. I don't want to do that. All right, and what we're going to do is just put positive on this side and negative on this side. I'm not sure if that's quite right. We'll see what the meter says. All right, so everything's configured, so let's throw the voltage on. Oh shit, I pressed the wrong button. All right, so let's try turning him on. All right, on he goes. So we've got 41 millivolts across the movement. So we're calling that VM. So VM equals 41 millivolts. And IM equals 18.6 microamps. 18.6 microamps. And so R in int, the internal resistance, equals V divided by I, VM divided by IM, equals 0.00041 divided by 0.0000186 equals, I have to make sure I press the right number of zeros into these things. I wonder if maybe I should just use scientific mode and exponents on the calculator. I've never really worked with exponents. Maybe I should upgrade. We'll see. Anyway, we're going to have 0.00041 divided by 0.000000186. Can't go that high. Equals 2.28K. 2.28K. And that agrees almost exactly, doesn't it? So we measured the resistance of the meter movement and we got this, and then we inferred it from the current and the voltage and we got the same reading, about 2.28 kilo ohms. Kick-ass! I think we're going to call that a wrap. There is more to do, but we can continue next week. So what we've covered today is internal resistance of the movement. That's 1L.4.1. That's how I'm going to write that up for today. And we will continue next week with 1L.4.2, which is the voltmeter. So I will duck over to the computer. I'll write up the notes, get the video delivered, and then we'll pick it up again next week. On Tuesday, I try to make Tuesday Learning the Art of Electronics Day. So let me throw you over the farewell, Ken. We'll wrap up. Oh, actually, no, that's right. I'll write up the notes now. Then I'll take you over the computer and I'll show them to you. And then I'll conclude the video, and then it'll be next week when we continue. Before I take you back over to review the notes, I just want to say, while I was writing up the notes, I discovered that I figured out that problem I was having earlier, understanding the thing where it said that they want you to work with a simple bare meter movement and not with a multimeter. And they say it's more fun to start from scratch. What they're talking about is working with a bare movement instead of actually using a multimeter as the meter movement. And then when they go on to say about the measuring that you do, you use the variable power supply and the digital voltmeter and such in order to measure the behavior of the bare meter. So in our case, this was the bare meter that we used as they requested, and then we did our measurements with our DVM and our variable power supply and our fixed resistor. So I just wanted to clear that up because I was confused about that earlier. But basically, the bare meter movement is this guy, and then the DVM is what we use to measure the current and the resistance and the voltage in the experiments that we did. So I'm going to go finish writing those notes. I'll be just a sec. All right. Well, here we are on the computer. I'll just, what am I going to do? Let's move this. I've got this book here at the moment. Anyway. So, let's open a web browser. And we're going to go to our notes. These are on the web at inthelabwithjj.com/wiki. These notes for this book are subscriber only material. If you want a subscription, please support me on Patreon. If you're a starving student and you want free access, send me an email and I'll hook you up with an account. So today we're going to keep on keeping on with the first part of the book. We're up to 1L, which is the DC Circuits Lab. So let's just open that up. Now, we will quickly run through what we already know, and then at the end of these notes is our new material plus the results from the experiment that we just did. So the purpose of this lab is to get you used to the breadboard and the multimeters. We will be learning Ohm's law, but we're not expected to find it surprising. Note that you measure voltages between points on a circuit, whereas you measure currents through a point in a circuit. Analog meters are known as VOMs, short for volt ohm millimeter. We won't really have much to do with those. We tend to use digital meters, which are known as DVM or DMM, short for digital voltmeter, or short for digital multimeter, as they're also known. Current measurement. To measure current, a DVM runs the input current through a small valued resistor and measures the voltage drop across that resistor. The small voltage that the DVM drops when measuring current is called the burden voltage. We did an experiment to measure the burden voltage. This was back before I had the convention of labeling anything that was a measurement in blue. So I haven't gone back and fixed that up, but maybe I will. I'll have to refer to the videos and dig it all up. It says here that you should be skeptical when measuring components in circuit. And it's best to disconnect at least one end of a resistor before taking a measurement. Some measurements here. This is a DVM's resistance measurement. We do a diode test. DVM's current, blah, blah, blah. Capacitance, transistor, beta, voltage divider. And we made the voltage divider, and we made the equivalent Thevenin circuit,
and we got the results. The voltage divider V open circuit is 7.52 volts. And again, for the Thevenin model, it's 7.51, which is very close. Essentially, these numbers agree. So the voltage divider and the Thevenin circuit are electrically the same. And this is where we're up to. So this is all new content now. There's a note here about the practical use of Thevenin models. You don't usually do what we just did, which is short the output of a circuit in order to measure its Thevenin resistance, which is also known as the output impedance, which we'll learn about soon. Apart from being slow to set up a measurement, I short circuit could be too large for the given circuit. Instead, we will get the same information using a method we can do on paper. That is, take all the parallel resistance of two or more resistances, making up the divider, and assuming that R source is ideal 0 ohms. So this is the circuit, this is the voltage divider, and this is the equivalent Thevenin model. So you have divider here, and you've got the Thevenin model here. And indeed, we tested this, and we built this, and they behaved the same. So now today, we're up to 1L4, which is Ohm's law applied to convert a meter movement into a voltmeter and ammeter. So a Thevenin model is a useful concept, but we won't be building them as we just did. We only built the model so we could get used to the concept. In this lab, we're going to build our own voltmeter and ammeter, but first we're going to measure the meter movement's internal resistance, R int. The meter movement is a current measuring device. The needle's deflection is proportional to the torque developed by the coil as it sits in the field of a permanent magnet. This torque, in turn, is proportional to the current through the coil. An analog multimeter, or VOM, volt-ohm multimeter, is just such a meter movement attached to a switchable resistor network. In the sections that follow, we will reinvent the multimeter. But before we do that, we do what we did today, which is to get the internal resistance of the movement. For our tests, we will be using a 100 microamp meter movement. I got that on AliExpress. The link is here. You could use 50 microamp. You could probably use 1 milliamp. So go your hardest. We make a circuit board J001 to attach our meter movement to. So I have just I've just begun with this. I'm going to label the circuits that I make, like this one, with the with a little thing that tells me what number it is, so that I can document them and then just throw them in the project box. And if I need to go rummaging, I'll know what I'm looking for. Now this board that I made, that I just told you about, J001, it has protection diodes installed per the recommendation in the book. So I've actually got parallel resistors in opposition to each other, so that anything over 0.6 volts will just get crowbarred. So it did ask what device that would behave like, and honestly, I have no idea. I would have said a short circuit, but maybe not. And I had planned to measure it, but I've already closed up the lab and cleared away. So we didn't check to see how those diodes affected the circuit when we went into territory that was greater than about 600 millivolts. We only used 41 millivolts in our experiment. Anyway, so yeah, the board has protection diodes installed. The first thing that we did in this experiment was measure the resistance of the 100 microamp movement directly with our DVM in resistance mode, and we measured 2.278 kilo ohms. So keep that number in mind. Doing the measurement affected the movement. It deflects fully during the test, but it doesn't seem to be damaged. So that was our just straight up multimeter resistance measurement. This is the test circuit that I built. and I built it on this board here that I made, special purpose board. Yeah, actually, give me 1 second. All right, so I just updated this, and there we go. So I say C J001. I'll put the documentation for J001 in soon, and it won't be read anymore when I've actually done that work. I'll do that later. But basically, this is the circuit for J001. And these are the values that we get. So we pump in 1 volt with a series resistance of 50k. Then we measure the voltage across the meter as 41 millivolts, and we measure the current through the meter as 18.6 microamps. We only used 1 volt for testing, which was enough. The series resistor was 50k. The voltmeter measures VM as 41 millivolts. The ammeter measures IM as 18.6 microvolts. So the measured internal resistance is the voltage across the meter divided by the current through the meter, which is 41 millivolts divided by 1.86 microvolts equals this, which I actually had to convert to something a bit smaller because I couldn't get that 6 in on my calculator. It exceeded the significant figures that my calculator can do. So I had to take off 4 zeros on each side and then do the calculation, and it came out at 2.204 kilo ohms. And our conclusion, the internal resistance that we measured is 2.278 kilo ohms, which is very close to the internal resistance that we calculated, which was 2.204 ohms. So it's good for two orders of magnitude. It's the same, and then it's off by just a little bit. So that's that. That's enough for today. I'll throw over the farewell cam. We'll wrap up.
And that's a wrap. So that was fun. We measured the internal resistance of our meter movement 2 ways. We did it directly with the resistance measurement of the multimeter, and we did it indirectly by calculating the resistance based on the voltage across the meter and the current through the meter. So that's it. We're done. Next week we'll continue on our journey, and we'll build a voltmeter. So until then, I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.